Hello everybody and welcome back. I happened to realize when I was putting together these notes that this is actually the 50th video of notes that I've put together for my classes this spring. And that's kind of weird to think about. Now, it's not like any of those videos is going viral or making me a YouTube star, but hopefully they have helped you to learn at least a little bit this spring. The good news is we really are getting pretty close to the finish line. There's only 3 weeks left, including this one, until we are at the end of the year. The past couple of weeks we've been talking about circles, and we're going to be continuing with that as we make our way through the rest of the year. Right now we're in chapter 12 of your book, and we're going to expand a little bit more on the ideas of circles as we look at two sections in your book today. You should remember from a couple weeks ago the term chord. A chord was just a segment that connected 2 points on a circle, and today we're going to find out a lot more about chords. I'm going to take a quick look at 4 rules that your book presents as theorems, even though they're all pretty much common sense. First off, it says here, within a circle or congruent circles, chords equidistant from the center or centers are congruent, and congruent chords have to be equidistant from the center. So if you've got 2 chords that are the same distance from the center of a circle, they have to be congruent. And if you've got congruent chords, they've got to be the same distance from the center. A couple of other theorems your book talks about. It says in a circle, if a diameter is perpendicular to a chord, it bisects the chord in its arc. And if a diameter bisects a chord, then it's perpendicular to that chord. So whenever you've got perpendiculars, the chord is cut exactly in half. And the last little theorem here, in a circle, the perpendicular bisector of a chord contains the center. If you know you got a chord that's perpendicular and it's cut in half, then the segment that does that has to go straight through the center. It's got to be a diameter. So here's just a quick summary of what all of those theorems say. Chords that are equidistant from the center are congruent. The diameter is perpendicular to a chord if and only if it bisects the chord, it cuts it in half. And the perpendicular bisector of a chord always goes through the center of the circle. If you're somebody that writes down notes, this might be a place to pause things and make sure that you got those down. But what we're going to do really is apply those rules. Many of the questions that you see that go along with this are really, really easy. And an example of that is this one. Look at the picture and see if you can figure out what is the value of x. And the answer is just 16. And it goes back to those theorems we were just going through. We said that if you have congruent chords, and here there's 2 chords in the picture that are both 36, they have to be equidistant from the center. Well, since one of them is 16 away from the center, the other one's got to be 16 as well. And here's another really easy problem. The question says to find the length of RS in circle O. RS would be the chord that's kind of diagonal over on the right-hand side. How long is that chord? And the answer is going to be 25. And when you go through this, the bottom chord, PR, if you add up 12 and a half on the left and 12 and a half on the right, it's going to be 25. And since RS is the same distance from the center as that bottom one, it's got to be the same, so it's 25 too. There are some problems that can get a little bit more involved than just copying a number in the problem or maybe doubling a number. When you have things that you can't just tell immediately what the answer is, what's usually going to happen in problems like this is you'll use the Pythagorean theorem. Remember a squared plus b squared equals c squared? That's how we're going to do the problems that you're looking at here. This first one, we're supposed to find out what r is. Well, if you look on the left-hand side, you're going to have a triangle where one of the sides is 3 centimeters. The bottom of that triangle would be 7 centimeters because it's half of the chord. And that's why I've got 3 squared plus 7 squared equals r squared. If you work that out, you add it up and you take the square root, you end up with about 7.6 for the answer. And it's just slightly different on this one. This time, that dashed line from A to B would be a radius of this circle, so it's got to be 15, the same as the radius that's given on EB. So I've got a triangle where 2 of the 3 sides are 11 and y, and the hypotenuse is going to be 15. That's why I wrote y squared plus 11 squared equals 15 squared. This time, since I'm trying to find one of the shorter sides, I have to subtract 15 squared minus 11 squared. I do the square root, and it's about 10.2. So when you're looking at chords, a lot of the time the answer is just something else that's already given in the problem, and if it's not, you're probably going to use the Pythagorean theorem. That's the first of the 2 main things we're going to be talking about today. And to get to the other one, I want to remind you of something else that we did a couple weeks ago. That was the idea of central angles. A central angle was just an angle where the vertex was right at the center of the circle. And we said a couple weeks ago that it always has the same measure as the intercepted arc. So like if the angle you're looking at in that picture was 60 degrees, the arc would have been 60 degrees as well. That leads into a new term that we need to learn this week, and it's the term inscribed angle. An inscribed angle is just an angle whose vertex is right on the circle. It's not at the center, and it's not on the interior anywhere. It's on the circle itself. So in this picture, angle B, or angle ABC, is an inscribed angle. And it turns out that an inscribed angle always measures exactly half of its intercepted arc. I put here that the measure of angle B has to be half the measure of arc AC. So like if I knew that AC was 50 degrees, then angle B would end up being 25. And again, the majority of the questions that you do are really very easy. Like this problem, I'm telling you that we have an arc that's 82. The question's asking you what's x. And all you do is divide by 2, and it turns out it's gotta be 41. This is one you need to think just a little bit about. It says in circle O, what's the measure of angle A? So think about that just a second, and then we'll talk about why it is what it is. Well, it turns out angle A has to be a right angle. And the reason why it does is if you think about it, since O is the center of the circle, then over at the top left, I've got to have a semicircle. And angle A is going to intercept that semicircle. And since it intercepts a semicircle, which would be 180 degrees, this has to be half of that. That's why angle A's gotta be 90. Here's an interesting question where it's asking you to find 4 different angles. You can see that this circle is divided up into arcs that are 106, 100, 90, and 64. And what we're supposed to do is figure out angle A, angle B, angle C, and angle D. So again, let's look through that for just a second and see if you can figure out how would you do all 4 of those angles. Well, I put in some extra lines here to try and make it a little bit more obvious exactly where those angles are. And if you look at angle A and you extend it so that it cuts through that circle, it should make sense that the arc that it's going to intercept, which happens to be BCD, is going to be 100 plus 90, or 190 degrees. The angle then's got to be half of that, so it's going to be 95. Pretty much all of these work the same way. The important thing is that the arc that they intercept, you actually have to add up two of the arcs in the picture to get. So like angle B, it's going to be 154 degrees that we have across from it. You divide that by 2, and angle B will be 77. Angle C, it's going to intercept the whole left side of our picture, which is 106 and 64. That adds up to 170. Take half of 170, and angle C is going to be 85 degrees. And finally, angle D, which is down at the bottom, it's going to intercept the two arcs up at the top, 106 and 100. If you put those together, you get arc ABC, and that's going to be 206 degrees. We divide that by 2, and that means that angle D would be 103 degrees. Now that's all the problem asked me to do, is just come up with those 4 angles. But I want to point out to you that those actually do have to be correct, because if you look inside the circle, we've got a quadrilateral. Remember, a quadrilateral has 360 degrees. Well, if I add up all the angles I found, yeah, they really do add up to 360. So yes, it makes sense that those should be correct answers. And that's what's new this week. We need to make sure that you do understand how to find lengths of chords and how they relate to other things in a circle. And you want to know that an inscribed angle is always half the intercepted arc. We're going to leave it at that for this week. I hope everybody's doing okay, and we will talk to you again next week.